Hello, everyone. My name is Javier Cembrano, recently graduated from Universidad de Chile, and today we'll present you our work on multidimensional apportionment through discrepancy theory, which is a joint work with José Correa, also from Universidad de Chile, and with Victor Verdugo from Universidad de O'Higgins. What are we talking about when we say multidimensional apportionment? Well, the apportionment problem is basically about allocating seats of a House of Representatives or any other representative body in a democracy. So historically, two dimensions have been considered when doing this. A political dimension, usually with political lists and parties, and a geographical dimension, usually clustering voters from nearby areas into electoral districts. But as modern societies become more complex, the representation of dimensions beyond these two is increasingly demanded. Some examples of this are the New Zealand's parliament, which has included ethnic representation for more than 50 years, as well as the parliament of the Federation of Bosnia and Herzegovina, which was proposed to include a division between three types of constituent people, the Bosniaks, the Croats, and others, and which led the Manch to coin the multidimensional apportionment problem as a relevant open question 8 years ago. A especially close example for us is the case of the recently elected Chilean Constitutional Convention, which included gender balance as an additional constraint. And I will use this example during the presentation in order to introduce the setting and the results of our work. So I would like to first think in one dimension. So let's suppose that we want to allocate H seats of a House of Representatives across some lists proportionally to their votes. And let's denote the votes obtained by each list L as B sub L. So for example, we could think that there are 10 seats to allocate and 3 lists with votes 43, 34, and 23. So what should be the apportionment in this case? Well, a natural first approach, known in the literature as the fair share, is to just assign each list the proportion of seats corresponding to its proportion of votes. So in our case, we have got 100 of votes and 10 seats to allocate. So one could just say, okay, let's multiply the votes obtained by each list by a lambda equal to 0.1. So list 1 should get 4.3 seats, list 2 should get 3.4 seats, and list 3, 2.3 seats. That's proportional and sums up to 10, so we're done. Well, nobody could disagree with the proportionality of this apportionment, but since we're talking about people who will be assigned to the seats, it is clearly not feasible to assign a fractional number to a list. So these kind of questions were the same that Thomas Jefferson and others were asking more than 2 centuries ago when they were thinking about how to allocate the seats of the recently created US House of Representatives. So the well-known Jefferson or D'Hondt method, called in this way because of its rediscovering by the Belgian Victor D'Hondt 86 years later, basically looks for an apportionment vector X such that its components sum up to H and such that there exists a strictly positive multiplier lambda such that the seats assigned to each list L corresponds to a downwards rounding of lambda times the votes obtained by the list. So these apportionments are guaranteed to exist, and for our previous example, would give 5 seats to the first list, 3 to the second one, and 2 to the last one, due to the downwards rounding of this scale vector using a lambda equal to 0.117. As you may imagine, this multiplier is not unique, but in fact, the apportionment vector is unique, and this is a general result. The Jefferson or D'Hondt method is widely used, and in particular is used for the Chilean elections in each of the 28 districts of the country separately. So as you may have noted, the previous method takes into account just one political dimension. But a natural way to consider the results of an election would be to also consider where was each vote cast. So what if we now disaggregate the votes obtained by each list across the electoral districts? So for instance, in our example, instead of consider the aggregated vote by list, we could instead consider a vote matrix where each row represents a list and each column represents a district. So for instance, if there were 2 districts in our example, the vote matrix would look like this. For example, the value of 23 in the vote matrix represents that list 2 obtains 23 votes in district 1. So as you can see, this provides a more global view of the election. And the goal of doing this is exactly to be able to construct a more globally proportional apportionment. And this was what Balinsky and the Manch proposed in 1989 in the so-called biproportional method. They considered as given certain values, also known as marginals, by list and by district. So we will denote as M sub L the seats that should be given to each list L, which are usually calculated through a one-dimensional proportional method or a divisor method. And we'll also consider as given a value S sub D for each district D, which is usually predefined by law. So given these values, Valinsky and Demange defined a biproportional apportionment as a two-dimensional matrix X such that each list L receives M sub L seats, each district D is assigned S sub D seats, and the proportionality notion is extended through one multiplier by list, lambda sub L, and one multiplier by district, mu sub D, both strictly positive, such that the seats assigned, the number of seats assigned to list L in district D corresponds to a downwards rounding of lambda L times mu D times the votes obtained by this list in this district. So once again, these apportionments are guaranteed to exist, and in our example would work as follows. If we wanted to give to each list the number of seats corresponding to their one-dimensional apportionment, meaning 5 seats to the first list, 3 to the second one, and 2 to the last one, and if we wanted to give 5 seats to each district, then some useful or proper multipliers for this instance are these in blue and orange. And why do I say that they are proper? Because when we scale the vote matrix with these multipliers, meaning if we multiply each component of the vote matrix by the multiplier associated to its row and by the multiplier associated to its column, we obtain this scale matrix that when rounded down gives rise to this apportionment matrix, which sums by row are exactly 5, 3, and 2, and which sums by column are exactly 5 and 5. So once again, these multipliers are not unique, but the apportionment matrix is unique. So in this point, you may imagine what is the main goal of our work, that is extending these notions of proportionality in 1 and 2 dimensions to arbitrary dimension. And in particular, I will present the 3-dimensional case in the context of the Chilean Constitutional Convention election, where, as I said, we want to include gender balance as an additional constraint. In the actual election, a local method was used, but a natural alternative would be to consider a global method trying to achieve global proportionality and at the same time give each gender half of the seats. So the definition of a 3-proportional apportionment in this context is in this case a 3-proportional tensor X, such that once again each list L receives the predefined number of seats M sub L, the same with each district D, and now we want each gender G to receive half of the seats, yes, supposing that H is even for simplicity. The proportionality notion is extended naturally by adding multipliers gamma G, strictly positive for each gender G. So now we want that the seats assigned to the candidates of list L and gender G in district D corresponds to a downwards rounding of the multipliers, the product of the multipliers corresponding to the list, the district, and the gender, times the votes obtained by these candidates. So this is the natural extension of the notion of proportionality that Valinsky and Demange introduced for 2 dimensions. But as you may imagine, this problem is not as, the results in this case are not as positive in the 2-dimensional case, and that's why possibly this problem remained open since 1989. Why is this? First, we proved 2 negative results. In first place, we proved that 3-proportional apportionments are not guaranteed to exist. And furthermore, we show that deciding whether a given instance admits or not a 3-proportional apportionment is an NP-complete problem. So these 2 negative results may be somehow discouraging. In particular, the first one, because it says that there are instances of the problem for which we are not able to find an apportionment simultaneously verifying proportionality and satisfying the marginals. However, in our main result, we are able to prove that there exists for every instance an apportionment satisfying proportionality and approximately verifying the marginals. What do I mean by this? If we consider values U1, U2, and U3, such that the sum of the inverses of these values plus 2 is less or equal than 1, then there exists an apportionment X verifying the following. These first 3 conditions mean that X approximately satisfies the marginals, meaning that each list L receives approximately M sub L seats with a maximum error of U1, each district D is assigned approximately S sub D seats with a maximum error of U2, and each gender G receives approximately half of the seats with a maximum error of U3. And the last condition is just that proportionality is satisfied for this apportionment. So as you can see, this vector U defines the maximum possible violations for each dimension, and some possible values for this vector are these 3. So for instance, when seeing the first vector, we are saying that there exists an apportionment X verifying proportionality and deviating at most 1 from each of the prescribed marginals. Or when looking at the second vector, we're saying that there exists an apportionment X verifying proportionality, giving exactly the desired number of seats to each list and deviating at most 1 for each district and at most 4 for each gender. So I would like to give a brief idea of how do we obtain this result. And the main observation here is that you may have noted in the two-dimensional case that the problem is really close to the matrix scaling problem. In fact, we are looking for a matrix basically which pre-specified sums by column and by row, but in our case, we are looking for an integer matrix. In fact, Gafke and Pockelshim showed more than 10 years ago that we can use an integer linear program very similar to the one used for finding matrix scalings, which linear relaxation, when solved, gives optimal solution that corresponds to biproportional apportionments. And since this problem in 2 dimensions is a transportation problem, we are able to conclude the existence of biproportional apportionment in that way. When we extend this integer linear program to 3 dimensions, we obtain this program shown here, which is no longer a transportation problem, but it is still a program of interest for our purposes. Its constraints are basically to satisfy the marginals, and its objective function is which allows to conclude proportionality. And why do I say that this is an interesting program? Well, we proved 2 important things. First, we extend the result in 2 dimensions in the following way. We prove that any optimal solution X of the linear relaxation of this program, if it is integer, then it is in fact a through proportional apportionment. But furthermore, we show that if this optimal solution X of the linear relaxation is not integer, then any rounding of it, meaning any bar X such that its components are equal to the downwards or upwards rounding of the corresponding component of X, verifies the proportionality condition. Of course, since X is visible for the problem satisfying the marginals, but when rounded, it may not satisfy the marginals. So we follow an approach based on the following. We solve the linear relaxation. If the optimal solution X is integer, then we keep it because it will be a proportional apportionment. And if it is not integer, then we round it and we will keep proportionality. But we round it in a certain way that we deviate as little as possible from the prescribed marginals. And in order to deviate as little as possible, we use an iterative rounding algorithm inspired in discrepancy theory, and specifically in Beck and Fiala's discrepancy theory. This allows to bound the deviations from each of the prescribed marginals and to conclude our main result. What we find more interesting about our work is this kind of unexpected connection between apportionment methods and discrepancy theory, which we think opens up new possibilities regarding the design of these apportionment methods. So I would like to finish the presentation by mentioning some important further results. In the first place, an important observation is that we actually study and prove the results in a more general setting, in 3 senses. First, we study the problem with an arbitrary rounding rule instead of downwards rounding. So instead of considering downwards rounding, we could consider, for example, nearest integer rounding, or the so-called Webster-San-Laguet method in apportionment theory. And the results extend naturally to this setting. This is important because different rounding rules lead to different apportionments in several cases. In particular, for our 1-dimensional example, the Webster-San-Laguet method would lead to an apportionment of 4, 4, and 2 seats instead of the one that you may remember of 5, 3, and 2. So it is important which rounding rule do we use, and our results are general in this sense. We also work with soft bounds in our paper instead of hard marginals, following both the settings of Palinsky and Yang in 1 dimension and the setting of Palinsky and Demange in 2 dimensions. They all use soft bounds for the number of seats that we want to assign to a given list, a district, or in our case to a gender. So for instance, we could, instead of say that we want each gender to obtain exactly half of the seats, we would say that we want each gender to obtain between a 40 and a 60% of the seats. And our results are still valid. In the third place, we work in an arbitrary dimension, not in the 3-dimensional case that was the one that I presented. And in dimension D, the sufficient condition over U in our main theorem turns into this sum being less or equal than 1. That is the same sum that we used for the 3-dimensional case, but for the arbitrary dimension case. In particular, it is important to know that when d equals 2, we can just take u1 and u2 equal to 0 because 1/2 plus 1/2 is less or equal than 1. And then we're saying that in 2 dimensions, there exists an apportionment satisfying proportionality and not deviating from the specified sums. Thus, we are recovering basically the existence result of Valinsky and Demarche that I mentioned at the beginning. So our general theorem for arbitrary dimension, in particular when applied in dimension 2, recovers this existence result by proportional apportionments, which is of Valinsky and Demarche. Finally, in terms of tightness, we do not know if our bounds are tight, in the sense that we don't know if they are the best possible bounds. Further improvements may be possible, but for instance, we do know that in 3 dimensions, bounds given by u1 and u2 equal to 0 and u3 equal to any constant k are not possible. And why is that a notion of tightness? Because the term here, in this case, turns into 1 plus 1 over k plus 2, which tends to 1 when k is bigger and bigger. So this is an expression that is arbitrarily close to 1, but still greater than 1, and for which we are not able to obtain that deviations for every instance of the problem. So that's a first notion of tightness. Further improvements of that bounds are a relevant open question of our work. So that was the presentation. Thank you very much for your attention.